Have you ever tried to imagine what a million years feels like? What about a billion? It's almost impossible, right? Our lives, our entire recorded history, are just a tiny blip compared to the age of our planet. Earth has been around for about 4.5 billion years, a number so huge it's hard to wrap our heads around. So how do we even begin to understand a history that long? Well, long before we had clocks or calendars, ancient people tracked time by watching the world around them. The sun rising and setting gave us days. The moon's phases gave us months. The changing seasons gave us years. These natural rhythms were perfect for farming, for planning festivals, and for recording the stories of our ancestors. But when scientists started looking at the Earth itself, the rocks beneath our feet, they realized they were looking at a story that was way, way older than any human story ever told. This is where the idea of geological time comes in. Think of it like a supersized calendar for the planet. Instead of days and weeks, geologists use eons, eras, periods, and epochs. These aren't just random chunks of time. Each one represents a major chapter in Earth's life story. It's like reading a massive book where each chapter describes a completely different world. So, how do scientists read this book? They look for clues buried in rock layers all over the globe, a field of study we call stratigraphy. Imagine you're baking a giant layer cake. The first layer you put down is at the bottom, and the last one is on top. Earth's rock layers, or strata, are kind of like that. The oldest rocks are usually at the bottom, and the youngest ones are on top. This simple but powerful idea is called the law of superposition, and it's a fundamental rule for reading Earth's history. By studying these layers, geologists can piece together what Earth was like millions or even billions of years ago. A layer of sandstone might tell them a desert once existed there. A layer of coal points to an ancient, lush swamp. And if they find fossils, that's when the story really comes to life. Fossils are like snapshots from the past. A trilobite fossil tells you that the rock it's in is from the Paleozoic era, a time when life was exploding in the oceans, but hadn't really conquered the land yet. Find a dinosaur bone, and you know you've jumped forward to the Mesozoic era, the age of reptiles. And if you find the fossil of a woolly mammoth, you're in a much more recent chapter, the Cenozoic era, the age of mammals. These specific fossils, called index fossils, are incredibly useful because certain species only lived for a specific window of time. Finding one of their fossils is like finding a date stamp in the rock. It helps scientists correlate rock layers across different continents, connecting the pages of Earth's history book from all around the world. But looking at layers and fossils only tells you what's older or younger. It doesn't give you an exact age in years. For that, scientists needed a new tooler kind of geological clock, and they found it in the 20th century with the discovery of radioactivity. Here's how it works. Some elements in rocks are unstable. They're called radioactive isotopes. Over time, they break down or decay into a different, more stable element. The amazing thing is, they do this at a perfectly steady, predictable rate. It's like a clock, that S been ticking away inside the rock since the moment it was formed. This rate of decay is called a half-life. That's the amount of time it takes for half of the original radioactive element to transform. For example, uranium-238 eventually decays into lead-206. This process has a half-life of about 4.5 billion years. Coincidentally, about the age of our planet. This method, called radiometric dating, is what gave us that mind-boggling number 4.5 billion years. It turned our relative timeline of older and younger into a concrete calendar with actual dates. The name comes from Hades, and for good reason. Early Earth was a hellish landscaper, molten ball of rock, constantly bombarded by asteroids. There was no oxygen, no oceans, just fire and rock. This violent beginning lasted for about 500 million years. Then came the Archean Eon. The Earth started to cool down, a crust-formed continents began to take shape, and water vapor condensed to form the first oceans. And in these ancient seas, something incredible happened. Life appeared. The first living things were simple. Single-celled organisms, like bacteria. They were tiny, but they were about to change the world forever. Some of them, called cyanobacteria, started performing photosynthesis, releasing a waste product that would transform the planet, oxygen. This leads us to the Proterozoic Eon, which means early life. The Great Oxidation Event happened during this time. The atmosphere, once toxic to us, slowly filled with oxygen. This was a catastrophe for much of the early life that couldn't handle it. But it paved the way for more complex life forms to evolve organisms that could use oxygen to create energy. Together, these first three eons, the Hadean, Archean, and Proterozoic, make up what we call the Precambrian. For nearly 4 billion years, life was mostly microscopic. All the dinosaurs, the flowers, the forests, the birds, and us all of that is squeezed into just the last 10% of Earth's timeline. This most recent eon is the Phanerozoic, which means visible life. This is when the Cambrian explosion happened. Relatively short period where life suddenly diversified into a dazzling array of new forms. We see the first fish, the first insects, and the first amphibians crawling out of the water and onto land. The continents were smashed together into a supercontinent called Pangaea. This is the one everyone knows and loves, the time of the dinosaurs. From the giant long-necked sauropods to the fearsome Tyrannosaurus rex, these incredible creatures dominated the planet for over 150 million years. The first mammals and birds also appeared during this time, but they were small, mostly hiding in the shadows of the giant reptiles. The Mesozoic ended with another famous Bangan asteroid impact that led to the extinction of the dinosaurs and cleared the stage for the next group to take over. And that brings us to our era, the Cenozoic, the age of mammals. With the dinosaurs gone, mammals diversified and grew, filling every corner of the globe. Grasslands spread, mountains like the Himalayas rose, and the climate cooled, leading to a series of ice ages. And in a small corner of Africa, a certain group of primates began to walk on two legs, develop larger brains, and use tools,